and also associate editor of IEEE TMI as well. So there are definitely more awards and services to be listed here. Shay is absolutely the rising star in the field of photoacoustic imaging and ultrasound imaging. And today, Dr. Berry is going to talking about listening to the sound of light to guide the surgery. Please join me and welcome Dr. Bell.
Thank you so much for the lovely introduction. It is my pleasure to be here to talk to you all about how we in my lab, the Photoacoustic and Ultrasonic Systems Engineering Lab, how we're listening to the sound of light to guide surgeries. So before I delve into the details of my research, I want to show you this video that captures an amazing sight that I once saw on my many flights around the world back when it was safer for us to freely travel without concern. While I long for those days, for now I'll just sit and reminisce as I watch videos like this. And if you're not familiar, it's the view of a thunderstorm from an airplane window. And as I watch these videos, I can draw many parallels between what I see and my lab's research. The first being the answer to the question of how can we listen to the sound of light? Well, we know that when lightning strikes, thunder is sure to follow. And that's because the light separates the air surrounding it, causing it to rapidly expand and contract and generate that loud roaring boom that you hear when you hear thunder. And this conversion of optical energy to acoustic energy is very much related to the photoacoustic effect, which is what we use in my lab as the basis of surgical guidance technologies. The second parallel is that I know that if I can see the lightning and hear the thunder, I can use the time differential between those two events to estimate how far away I am from the thunderstorm. But if there are tall buildings or mountains in the way, then my distance estimates may not always be accurate. And this is very much related to the concept of acoustic clutter, which degrades our image quality and makes it difficult sometimes for us to use the desired photoacoustic effect to guide surgeries. The third and final parallel is that as you watch this video, you notice that the lightning does not illuminate the entire sky at once. It's modulated throughout the sky. And this is similar to how we in my lab are modulating our light sources throughout the human body in order to guide various aspects of surgeries that occur on different organs throughout the body. So as an outline of my talk, I'll first give you some background information to understand the core photoacoustic technology that we develop. And then I will transition into discussing some applications of this technology to surgical guidance. I'll then talk about the heart of the acoustic clutter problem that makes it difficult for us to interpret images, and then transition into two techniques that we're developing in order to address acoustic clutter. The first is our deep learning approach, and the second is our spatial coherence approaches. And then I'll end with a summary and outlook. So to get started, let's look at the ultrasound system architecture. And we start here, not only because my lab does both ultrasound and photoacoustic imaging research, but because these two systems are naturally intertwined. So the ultrasound system architecture has three main components. The first is a scanner, which houses much of the electrical and computing hardware of the system. The second are these ultrasound probes which act as transmitters and receivers of the acoustic wave. And the final component is the monitor that's used to display images on the screen. The way that these three components interact is that the scanner transmits electrical pulses to the ultrasound probe, which contains an array of piezoelectric elements that convert the electrical signals into mechanical pressure waves that are propagated into the body. These mechanical pressure waves then reflect off of different structures in the body and return an echo to the ultrasound probe, which uses those same piezoelectric elements to now convert the mechanical pressure wave into electrical signals. And then those electrical echo signals are sent to the scanner, which receives those signals and sends them to an onboard computer for processing. The first step in the processing chain is beamforming. You can think of it as the first line of software defense against a poor quality image. After beamforming, the signals may undergo some more post-processing, such as scan conversion, log compression, and filtering, And finally, the image is ready for display on the monitor. Now let's talk about photoacoustic imaging, which can be thought of as ultrasound imaging with a laser. So generally, if I want to image a photoacoustic target, I can do so by using the same ultrasound probe that's used for ultrasound imaging. I would transmit laser light toward the target, which absorbs the light, undergoes thermal expansion, and generates a sound wave that has an initial pressure distribution that's defined by mu sub A, which is the optical absorption of the target, the Gruneisen parameter, gamma, which defines thermal properties of the target, and the laser fluence, which is defined as the energy divided by the incident surface area. So I generate this initial pressure distribution that propagates toward the probe, and then the same piezoelectric elements that are used to convert mechanical pressure waves into electrical signals for ultrasound images can do the same process to create photoacoustic images, and then the process is fairly similar to what you saw in the previous slide, where these signals are sent to a scanner, which receives the signals and sends them to an onboard computer. We see again this critical beamforming step that's at the heart of both ultrasound and photoacoustic imaging. Then we would do some additional post-processing, and finally the photoacoustic image is ready for display on the monitor. The nice thing about photoacoustic imaging being ultrasound imaging with a laser is that we can interleave ultrasound and photoacoustic images to improve the surgical experience. And just to bring this concept home a little further as to why we're using photoacoustics, despite this wide array of imaging techniques that already exist for interventional imaging, such as X-ray imaging, CT imaging, ultrasound, and MRI, well, we're using photoacoustic imaging because it exploits a different tissue property from all of these other existing interventional systems. And that's the property of optical absorption. So photoacoustic imaging is beneficial for targeting any structure that has a higher optical absorption than its surroundings. This is true of blood vessels, as well as metal implants that may be inserted into the body, as well as contrast agents that can be injected into the body. So in summary, photoacoustic imaging has the potential to provide new information for surgical guidance. And on top of that, it shares many of the same benefits with ultrasound, such as its ability to provide real-time information, it not using harmful ionizing radiation, and it being portable. From a historical perspective, photoacoustic imaging has made an impact and has shown remarkable promise in several applications, including small animal imaging, where you can see the vasculature in this mouse brain, as well as superficial vessel imaging, where you could see the vasculature in the palm of this person's hand. It could also be used in molecular imaging to determine the uptake of a drug in a particular region over time. And it could be used for intravascular imaging, where you could put an ultrasound and optical fiber integrated together inside the vessel lumen, spin it around to get images like the ones that you see at the bottom. And in particular, what you're seeing is a photoacoustic image of a metal stent, because remember, photoacoustic imaging does a good job at visualizing metal. And you're seeing how well this stent is situated within the vessel lumen. And the vessel lumen is provided by the ultrasound image. So we can see whether stents are rightly sized for a vessel lumen. The common system design among these applications is to attach light sources to acoustic receivers, as you see in the bottom left, and as is also the approach that was obtained to get the top two images on the right. Or we can have a light source that is located at a fixed distance from the acoustic receiver, as you see in the top left. The novelty introduced by my lab breaks this traditional rigidity in system design and adds more flexibility by separating the light source from the acoustic receiver and instead attaching it to a surgical tool. One reason we do this is because metal has a high optical absorption, as you can see this image of the metal stent. And so it affords us the opportunity to see both a metal tooltip and vasculature hidden by tissue during surgery, much like you see the vasculature in the palm of this person's hand. This combined information is useful to provide surgeons with the level of detail they would need to avoid accidental injury to major blood vessels during surgery, which can be very catastrophic and can potentially lead to patient death. The first working prototype for this concept was demonstrated by my lab for neurosurgery. We built a specialized light delivery system to surround a neurosurgical drill that you see me holding here. Then we have these mock surgical environment where the two black lines represent the internal carotid arteries. When the prototype enters the surgical field, we see the tooltip and its relationship to the mock arteries in the accompanying photoacoustic image. This result gives us confidence to correlate what we see in the photoacoustic image with what is actually taking place in the surgical field. But in a real surgical environment, the structures are hidden. So we added a layer of bone to increase the complexity of the mock surgical field. And in doing so, we see that the same information is present. That information is that it is safe to proceed when we only see the drill tip in the photoacoustic image. And otherwise, we don't want to proceed, or we want to proceed with caution when we see that the drill tip is located next to one of these major vessels. Let's take a step back and look at the bigger picture for this prototype design, which was developed for minimally invasive surgery that is performed through the nose to remove pituitary tumors. Our proposed design features flexible fiber probe separation rather than the more rigid approaches that I mentioned on a few slides earlier. And in offering flexible fiber probe separation, we have also this local light illumination by attaching an optical fiber to the surgical tool that's inserted through the nose. And then we can generate the photoacoustic effect and sense the resulting sound wave with an external ultrasound transducer that was initially proposed to be placed on the temporal region of the skull. So we see that this design requires both optical and acoustic engineering in order to make it work. The optical engineering can be studied with optical simulation software that tells us details about the light profile sizes and optimal placement for the optical fiber relative to tool shafts. We can also use the simulations to determine how far fibers should be set back from the tool tip, or how many fibers we should use, or what the profile would look like as a function of distance from the tissue surface. And this last option is what you're seeing here. From the sample photographs on the right, we get a nice confirmation that the dimensions and the shape of the light being produced by our experimental prototypes closely match our ZMAX simulations as a function of distance from the tissue surface. Now, I mentioned on the previous slide that the external ultrasound probe used to detect the resulting acoustic response generated from this design was initially proposed to be placed on the temporal region of the skull. After additional exploration, we learned that the temporal region is not the only possible location for this system design. We came to this conclusion based on a series of simulations and experiments performed with the same cadaver skull, which you see a 3D reconstruction of here. Now you're seeing the result of a K-wave simulation of a photoacoustic source placed within the location of the internal carotid artery. External receivers were then distributed around the skull, and they were used to measure the maximum pressure received by each sensor, which is represented by the colors. This result that you're looking at shows us that there are additional possible ultrasound probe placements based on the location of maximum pressure. Those locations are the eyes and the nose. We validated these simulation results with the experimental setup that you see here using the same cadaver skull that was simulated. The commonality among these setups is that we have an optical fiber in the nose to illuminate the location of the internal carotid arteries that we don't want to injure during surgery. Because photoacoustic imaging is the union of optics and acoustics, we care about both light delivery designs and acoustic receiver designs. And so that's why the ultrasound probe is placed in the different locations indicated by the arrows. The top left shows the ultrasound probe on the initially proposed temporal region of the skull. The top right shows the ultrasound probe placed in the newly identified nasal region. And the bottom images show the ultrasound probe placed on the newly identified ocular region, both in the absence and presence of eyes that were inserted into the skull. From this experimental setup, we obtained the images shown here, which represent photoacoustic results in color overlaid on grayscale CT images. we see that the location of the photoacoustic signals match the locations of the right and left internal carotid arteries. And then if we take a step back and look at what we actually did, we noticed that this combination of simulations and experiments highlights a new possibility of performing patient-specific simulations to determine optimal probe placement prior to the initiation of a surgery. This concept can also be applied to robotic surgeries, such as surgeries performed with the Da Vinci robot, where the surgeon would sit at a master console and the subtle motions of the surgeon's hands translate to motions of the robot arms, which are holding surgical tools that are inserted through keyhole-like incisions into the patient. Our goal is to bring in a miniaturized photoacoustic imaging system to perform photoacoustic guided surgery by attaching a specialized light delivery system to any one of the Da Vinci tools. Here is an example of what the surgeon sees when looking through that master console and sweeping the surgical tool around the surgical space to identify where to make an incision. The inset shows corresponding photoacoustic images. And from this example, we see that there are photoacoustic signals in one region and no photoacoustic signals when the surgeon moves away from that region. We developed this concept in particular for guidance of hysterectomies, which is one of the most commonly performed procedures with the Da Vinci robots. This procedure is performed to remove the uterus, and it requires severing of the major blood supply to the uterus, which are the uterine arteries, shown in red in this diagram. And we want to sever the uterine arteries while keeping the ureters, which are shown in yellow, intact in order to preserve urinary function. One challenge with this surgery is accidental injury to the ureters given their close proximity to the uterine arteries. And we are exploring photoacoustic image guidance to overcome this challenge. We are also working on mapping the information provided by photoacoustic imaging to an auditory output that you can hear, which was a request from one of our surgeon collaborators. And I'm going to show you a demonstration of that, but if you have an aversion to somewhat gory images, then you might want to turn your head for this next slide. So here is an example result showing the auditory mapping demonstrated with a human cadaver during an open surgery, where the ureter is filled with contrast agent methylene blue, and the tooltip is made of metal, which can be seen in the photoacoustic image along with the ureter to get photoacoustic images like the ones you saw in the previous few slides. We can then measure the tool to ureter distance and map that distance to a sound. And here's a demonstration of that. So you can see that when the distance measurement is below a certain threshold, that is the only time a surgeon would be alerted. And with this contribution, the surgeon doesn't have to only look at images to determine proximity to a major structure that we do not want to injure. And the beeping sound that you hear, it rises in frequency as the critical distance decreases and becomes significantly more critical, similar to the parking sensors on modern automobiles. So we see there's a wide range of possibilities, from visual to auditory cues to deliver information to surgeons once we generate proximity information based on the photoacoustic data. We can also use photoacoustic imaging to deliver information for other interventional applications, such as to assist with needle tip detection in challenging cases of ultrasound-guided liver biopsy. In these challenging cases, it is difficult to see the needle tip in the ultrasound image due to body habitus. And we want to use photoacoustic imaging to increase confidence of needle tip locations, regardless of the surrounding body habitus, and ideally deliver an image that looks like this. We can do this by inserting an optical fiber into the hollow core of the biopsy needle. We can also relieve the operator from searching for this tiny dot in the liver by attaching a robot arm to the ultrasound probe. And we tested this concept in the controlled experimental environment shown here, where we have an optical fiber inserted into a needle, which is rigidly attached to a translation stage. And here's a video demonstration showing the system in action for ex vivo liver tissue, where we have the needle being advanced into tissue, And the ultrasound probe is held by a robot, and it's making subtle motions to keep the probe centered on the needle tip. Then if we're nowhere near our biopsy target, we can overtake the robot, search for where that target is, and then release. And it's the robot's job to find that needle tip again while we guide our needle toward the identified biopsy target. Now, if we look at the photoacoustic images, which are shown on the right, and a segmentation of the images shown on the left, with the green line representing the image center, we see that initially it was very difficult to find that signal, but eventually the robot keeps searching and the signal with the highest SNR is confidently centered in the image. From this demonstration, we can appreciate how artifacts are problematic both for us as humans looking at these images and trying to interpret them, as well as for robots that are relying on these images to determine their next move. And this is the motivation for our novel beamforming approaches, because sometimes standard beamforming approaches like what you saw in the video fails. Our two alternative approaches that we are exploring in my lab is first a deep learning approach that I'll talk to you about, and second, a real-time coherence-based beamforming approach that I will also talk to you about. To understand our deep learning approach, let's start with the case of visualizing a wave propagating from a point source. And this could be the same kind of point source that's produced from a needle tip using the setup on the previous demonstration. So this wave propagates outward spherically from the source, and then the wavefront is recorded by each piezoelectric element in the ultrasound transducer, producing what we call raw channel data that looks like this. Our goal in the whole image formation process is to create an image that ideally looks like the source that created the raw channel data. But when we apply today's beamformers, we might instead get something that looks like this, where the shape is distorted and the source appears at an incorrect depth. And then we might have artifacts to the left and right of the source. One reason we see these deviations from what we expect is because of a fundamental flaw with current beamformers. They make assumptions about wave propagation that are not always true. For example, we know that the time it takes to receive the signals is related to the depth of the point source through the speed of sound in the medium, similar to how I can estimate my distance from the thunderstorm. We assume that the speed of sound is constant when we reconstruct these images, but it is not constant when there are multiple tissue layers with varying sound speeds and also varying sound speeds between each different patient. And so what happens is that artifacts are produced when the acoustic environment significantly deviates from our assumptions. And not only incorrect assumptions about speed of sound, but also incorrect assumptions about constant density, incorrect assumptions about the absence of multipath reverberations, as well as incorrect assumptions about the absence of acoustic reflections. And to help you appreciate why this in particular is problematic, here we have another simulation showing one source and a reflector in the field. So when this source propagates its wavefront outward spherically, once the wavefront encounters a reflector, notice that another wavefront is produced. And when we record the resulting channel data, we get the image that you see on the left. And then when we beamform the portion of the image that's highlighted by the red box, we get the image that you see on the right. And so from this video demonstration, we know where the source is originated from, and we know what caused the artifact, and we can appreciate a definition of artifacts as the mapping of signal sources to the wrong location. Our goal with our deep learning approaches to beamforming is to map signal sources to the correct location, where we would want to input into our networks the raw channel data like you saw on the previous slide, and then we get some outputs and create an image from the learned parameters. And when we train these networks, we train them with simulations similar to the simulations that you saw on the previous few slides. We can appreciate from the simulations that you saw that the curvature of the recorded wavefront depends on the distance of the source from the receiver. So essentially, sources that are closer to the receiver will have a different wavefront shape than sources that are farther away. And this means that there should be a unique curvature and shape of the wavefront for each depth of a source in an image. And our goal is to use state-of-the-art computer vision techniques, such as deep learning, to learn this unique shape-to-depth relationship for photoacoustic sources. And then all other sources are categorized as artifacts, or all other wavefronts, I should say, are categorized as artifacts. So unfortunately, deep learning is not an exact science. So it did take some trial and error for us to see if this was a good idea. And we settled on a network that we published in IEEE Transactions on Medical Imaging in 2018. The input of this network is raw channel data, and it has three outputs. The first is a classifier of a detected wavefront as a source or an artifact. The second is a confidence score. And the third is a bounding box location that identifies the peak of a wavefront that's detected. We can vary multiple parameters while training our networks, and one of those parameters is the noise level. So we can see on the bottom an example of us starting with a noiseless case and then gradually adding more and more noise up until we have negative 21 dB channel SNR. The bar graph on the top shows source and artifact classification accuracy in shades of blue as a function of the noise levels, which is listed on the x-axis. We see that we have perfect classification accuracy in the noiseless and in the negative 3 dB SNR case, and then accuracy starts to degrade as noise increases. However, what is remarkable and exciting about this result is that we have greater than 82% classification accuracy at negative 15 dB channel SNR. But when you and I look at that negative 15 dB channel SNR image, it's very difficult to see where the source or the artifact is located. So it's remarkable that the network was able to detect anything. And then as noise level increases, the classification accuracy plummets, and there are more missed sources and missed artifacts, which are shown in shades of yellow. And then the associated ROC curves on the right show the same trend for both sources on top and artifacts on bottom. We achieve perfect classification for the noiseless case, and then the classification performance starts to degrade as the ROC curves transition farther away from the ideal curve as noise increases. So we basically see the same information, just two different display formats. Another parameter that we can vary is the location of the sources in our simulation. And then we can take the wavefront location identified by the bounding box, which if you remember, it's one of the three network outputs, and we can compare that location to the ground truth source location from our simulations, which we know because we simulated it. Then we use the comparison between these two locations to compute a location error, which is shown on the y-axis of these two plots for the axial and lateral image dimensions. The x-axis of these plots show the same noise levels from the previous slide, and we see that our spread is fairly consistent, and so is our mean absolute error, which is on the order of 0.1 to 0.2 millimeters. This result is remarkable because it shows us that we have sub-millimeter error, and this sub-millimeter error is actually within the resolution of the imaging system. So it's within the bounds of the physical limits of how well we can localize a target. And we'll see why this is important later. But for now, I want you to also be aware that there were other parameters that we varied, such as the number of sources and artifacts, the speed of sound, and the acoustic receiver model. I don't have time to show you the results of all of these, but I do want you to know that we varied multiple of these parameters. And then once we varied it and trained our networks with these variations, we then had a network that we were comfortable with testing on experimental data. And then we came up with this nice controlled experimental environment where we have 4 point sources. They're actually brachytherapy seeds that when viewed in the orientation shown, they appear as point sources in the image. And then we can selectively illuminate the number of sources. And so that's how we control how many sources should appear in our channel data. So the middle photograph shows us selectively illuminating 2 sources, and the channel data on the far right shows the result that we get when we selectively illuminated 3 of the sources. Zooming in on this channel data result, we see that although only 3 sources were illuminated, there are 4 wavefronts in the image. And then when we use today's beamformers to create the image, it does look like there are 4 sources or 4 brachytherapy seeds in the image, which you can imagine would be not a good result if a brachytherapist is using this to guide the treatment plan. So what we want to do is to return to the raw data that created this image, pass it through our well-trained network, and get an image that we call our CNN-based image that looks something like this. This image has no artifacts, simply because we choose not to display anything that the network identifies as an artifact, and we only display what the network identifies as sources. This image also has high contrast because we choose the amplitude with which we display the sources. And the network has high resolution at depth because the size with which we display the sources are related to those location errors that you saw on the previous slide. And this is remarkable because the location errors, although I didn't show it, you saw that the spread was fairly consistent as a function of noise level, but that spread also remained consistent as a function of the depth of the point source. So here's an example that shows us why our network maintaining a high resolution at depth is a major advantage. We performed a cardiac catheterization procedure to demonstrate this and get the image that you see on the far left by inserting an optical fiber, this time into the hollow core of a cardiac catheter. And then this catheter is placed in the femoral vein and guided toward the heart, typically using fluoroscopy. So what you're seeing now is the catheter in the vein at a depth of 8 centimeters. And traditionally, photoacoustic images are known to have poor resolution at this depth, especially when we use the low frequency ultrasound probes that are needed to even get images at this depth. And so we can't really rely on traditional imaging methods to determine where our catheter tip, where exactly it is located. So what we want to do with our deep learning approach is return to the raw data that created the traditional image, which you see in the second panel, pass it through our well-trained network, and you see one of the outputs of our network identifying the bounding box of the peak of the wavefront that should appear at the depth of 8 centimeters, and then use the output of the network to create the CNN-based image. And this CNN-based image tells us very clearly where our catheter tip is located. And then we can also learn something from the network output and try to understand what the traditional image was trying to tell us by overlaying the CNN-based image on the traditional image. And then we start to get some insight about where that catheter tip was located based on the traditional image information. Now, the previous result was in the vein, and again, our goal was to make it toward the heart, and we did that. And I also mentioned that these cardiac catheter tips are currently tracked by fluoroscopy during an interventional procedure, and you see an example image of a fluoroscopy image here. And one challenge with these fluoroscopy images is that they don't provide depth information, much like the depth information you saw on the previous slide. Another challenge that is well known is that it utilizes ionizing radiation, which could be harmful to patient and operators. While ultrasound is widely available and it can show us how deep the catheter tip is located from the body's surface, as you see in the middle panel, you also see on the bottom that ultrasound has a failure point because the catheter tip blends into the background when it touches tissue. So when we insert an optical fiber into the hollow core of the cardiac catheter, as you saw on the previous slide, and we make the photoacoustic images within the beating heart, we get the exciting results shown on the right, telling us that we can see catheter tips in vivo photoacoustic images regardless of their contact with tissue. And we can see this without requiring ionizing radiation. This result alone implies that we can potentially use photoacoustic imaging to replace fluoroscopy. My vision in particular to replace fluoroscopy is to have the system as unobtrusive as possible. So we want wireless ultrasound probes attached to body-mounted robots, and we would use miniaturized laser systems to deliver this technology. One challenge though with the miniaturized laser systems is that they tend to produce low laser energies. And why exactly is this a challenge? Well, here is an example of what would happen when tracking a catheter tip using the system that I previously introduced you to when we have a low laser energy. Essentially, the system fails to find that catheter tip, particularly with the conventional amplitude-based beamforming approaches, which are the traditional approaches that you've been seeing up until this point. We also saw that deep learning works for some cases of high noise, but we also saw that there is a point when the noise is too low even for the deep learning approach. And this is one reason why we are exploring other approaches, such as the coherence-based approach that you see here, where we can take the same raw data that produced the amplitude-based images on the left, pass it through a different beamforming chain that calculates spatial coherence, and then displays the spatial coherence information. We see that the system works beautifully for this case. And so therefore, it is highly promising for using coherence-based beamforming with these miniaturized low laser energies in the surgical or interventional suite. So now you may be wondering, why is coherence-based beamforming so successful? Well, let's start, to answer this question, let's start with a contrast to why the amplitude-based beamforming approach fails. So we would have a point source that generates a spherically outward propagating wave, as you saw in the simulations. Now you're seeing a static representation of all of the events at once, where the gray rectangles represent 5 elements in our ultrasound receiver array, and the elements receive the wavefront from the point source propagating toward the array. The signal recorded by each element channel is slightly shifted relative to its neighbor, and that's because of the subtle time differential caused by the middle sensor being close to the point source and the outer signals being farther away from that point source, or the outer sensors being farther away from that point source. We can then apply system time delays to account for this time differential and align all of the signals originating from the same source. And then we would sum across the channels to get one larger signal corresponding to the source that created the recordings on the multiple channels. And this is how we perform conventional or traditional amplitude-based beamforming. Now, the challenge with this approach is that there could be a high amplitude signal recorded by only one of the channels, and this could be caused by random noise or a reflection artifact or simply electronic noise in the system, all creating poor channel SNR. And this signal maintains its presence after delays are applied and after the summation step is performed. So what if we take a step back and replace the sum with a cross correlation operator? Because although the signals may have high amplitude, resulting in that signal that makes it difficult for us to determine what we're looking at, we would expect the high amplitude signal, shown in red, to be uncorrelated with the neighboring channels. And by contrast, signals from the same source would instead have a high correlation. This is the basis for coherence-based beamforming, which was the topic of my PhD dissertation. I studied this concept for ultrasound imaging, and here are some images that are produced with this beamforming concept, where we show traditional amplitude-based delayed sum beamforming on the top, and the coherence-based beamforming, which is also called short-lag spatial coherence beamforming, more specifically called short-lag spatial coherence beamforming, or SLSC imaging. That's shown on the bottom. We see that with SLSC imaging, we have a better delineation of the boundaries within the beating heart, as you see here. We get rid of all this acoustic clutter from these high amplitude artifacts, but low spatial coherence artifacts. And so we could see the truly coherent tissue boundaries much better. The same can be said of these vessels within the liver. We can see them more clearly. We can even see the profile of the fetus, such as the nose, the mouth, and the fetal heart more clearly with the coherence-based approach in comparison to the amplitude approach. And we can even see these smaller vessels surrounding the carotid artery more clearly with the coherence-based approach. After developing SLSC imaging as a graduate student, I applied the SLSC beamformer to photoacoustic data during my postdoc. And in this example result, you are seeing some of the first work exploring this concept as a function of laser energy, or more accurately as a function of fluence, which, if you remember, if you didn't know, it's the laser energy divided by area. From these early results, I recognized the potential for low laser energies. But there were also some unexplainable trends, which led me to question the fundamental theory. So in summary, spatial coherence theory existed for ultrasound and served as the basis for ultrasound short-lag spatial coherence imaging. Then it was tested by multiple groups with experimental data for ultrasound. And in parallel, the application of spatial coherence to photoacoustic imaging was tested with experimental data. However, the same theory did not work for photoacoustics. After returning to fundamental principles as an assistant professor, my graduate student and I arrived at this expression in the blue box, which can be compared to the analogous ultrasound spatial coherence theory expression shown above it. We see that both expressions represent a Fourier transform, and the ultrasound expression in particular relies on a transmit ultrasound beam H, but there is no transmit ultrasound beam in photoacoustic imaging. So we have this additional phase term on the outside of the Fourier transform that accounts for the receive beam steering that we still implement when we make photoacoustic images. And this comparison helps us to understand previously unexplainable trends, and it also indicates that there are some additional terms to exploit for coherence-based photoacoustic image optimization. The expression on the previous slide was derived by approximating photoacoustic imaging as a linear system, where we start with the photoacoustic spatial covariance, which is defined as the correlation of the pressure field at two lateral receiving positions x1 and x2. The acoustic pressure measured from a photoacoustic target is then defined as the random distribution of spatially incoherent absorbers multiplied by an initial pressure distribution, which can have an additive noise term, multiplied by spherical, or the expression for spherical propagation from the source to a point on a receiver. And then after deriving the math, we get this expression at the bottom of the slide, which matches the expression that you saw on the previous slide in the blue box on the previous slide. This final expression says that the photoacoustic spatial coherence is equal to a phase term multiplied by the Fourier transform of an initial pressure distribution squared plus some scaled noise terms. This expression, it can be considered as the Van Sittert-Zernike theorem applied to photoacoustics. This is the first time that this theorem has been related to photoacoustic imaging. And for those not familiar, this is a theorem that relates the coherence of an incoherent source to the Fourier transform of that source. In this case, the requirement for an incoherent source is satisfied by newly recognizing that a photoacoustic target can be modeled as a random distribution of spatially incoherent absorbers. This model can then be applied both in the presence and absence of noise to predict spatial coherence functions. Here are examples of predictions in blue in the presence of noise compared with K-wave simulations, which were the same simulation method used to identify the optimal receiver locations for neurosurgical guidance. And those results are shown in red, and the experimental data that we compared to is shown in yellow. The x-axis shows the spatial lag between two receiving points presented as a percentage of the received aperture. And the y-axis shows the spatial coherence either predicted by theory or measured from simulated or experimental sensor data. This result makes sense from the Fourier transform expression on the previous slide, which presents the lag dimension, as a spatial frequency. Therefore, wider in space means shorter in spatial frequency. In particular, the smaller target has a fairly long coherence length, and the larger target has a smaller spatial coherence length. And if you're not familiar with the term coherence length, it is the distance up to the first zero crossing, which also defines what we call our short lag region. We can integrate coherence functions within the short lag region to obtain 1 pixel in the short lag spatial coherence image. So how exactly do we transition from a spatial coherence function to an Slsc image? Well, the left plot shows lag as a percentage of the received aperture on the x-axis, with the predicted and measured spatial coherence on the y-axis from multiple positions along one lateral line in the image dimension space. The theoretical predictions are shown in blue and compared with experimental data shown in yellow. After integrating each coherence function over the short lag region, we get the lateral profile shown on the right, and the dashed line on the right represents the specific location in the image space that produced the corresponding spatial coherence function. So taking this approach, we get a lateral profile that reveals a coherent point target. And now we're seeing the images that we get when this process is repeated, not only across the lateral space, but also for multiple axial depths. So returning to the coherence functions on the left, we now have the understanding we need to appreciate that the highest spatial coherence occurs at the target center, and we have lower spatial coherence anywhere off center from the target. We can also appreciate that our theory matches experimental data very well, particularly at lower spatial lags. So after creating images like the ones you see here, these SLSC images can be used to compare and measure contrast in theoretical and experimental images. And that's one of the beauties of this theory. I'm going to show you some results of this comparison, but before I do, I want to show you another trend that follows nicely from the mathematical theory that was previously unexplainable without this theory. This trend shows that the light profile size impacts the spatial coherence measurements. So here we are predicting spatial coherence functions in the absence of noise for multiple target sizes, which are represented by the different colors. On the left, we performed this prediction for a light sheet that illuminates the entirety of the photoacoustic target. The x-axis shows the spatial lag between two receiving points presented as a percentage of the receive aperture. And the y-axis shows the predicted spatial coherence. We see that coherence length gets smaller and smaller as the target gets larger for the light sheet illumination. And then if we shrink the light profile down to a Gaussian beam, we see that a similar trend exists only up until the point where the Gaussian beam size is similar to the target size. After this point, the coherence length then becomes dictated by the size of the light beam, and the multiple coherence functions for the different target sizes overlap each other. Now we can use predictions and experimental results to measure contrast, as I promised. We make the theoretical measurements in the presence of noise, and that's why we have this large variation shown by the shaded regions. The x-axis shows target diameter, and the y-axis shows contrast measured initially with a light sheet, which is shown in gray, and then the light profile size was reduced to a 5mm Gaussian beam with the results shown in blue, and then to a 3mm Gaussian beam with the results shown in red. The data points show our experimental measurements, which overall match very well with theory. Once we shrink our light profile size, especially for the larger targets, we see that we can boost our contrast simply by making the light profile size smaller. We can also look at target diameter on the x-axis and the measured target full width at half maximum on the y-axis. Ideally, this would be a one-to-one relationship, which is shown by the dashed line. We see that the largest light source has the closest representation to the ideal line. And then as the light profile size decreases, the measurements start to deviate from the ideal line. So we see from this result that we can improve boundary delineation with a larger light profile. However, we saw on the previous slide that limiting the size of the illumination beam provides higher SLSC contrast. So we have an expected trade-off between target contrast and target boundary delineation when adjusting our light profile sizes. And we can resolve this trade-off simply by using a smaller light beam to improve contrast and then scanning across the target to see the full boundary. And I'll make one final point about these results, which were obtained in the absence of optical scattering. Although we know that light scatters in tissue, we can still maintain some control over the light beam size and limit this optical scattering by placing targets as close to the structure of interest as possible. What you saw in the earlier slides is our main approach to light delivery for photoacoustic guided surgery. Now we have this nice theory that matches experiments very well. What can we do with it? One thing that we can do is we can explore how light profile designs affect the SLSC image contrast and resolution in a purely simulation environment. Typically, what we would have to do without this theory is build multiple prototypes and perform experiments with them as described in these 3 publications. Now we have a simulation environment to short circuit this requirement. We can also use this theory to enhance tooltip contrast in photoacoustic images for surgical guidance by optimizing which lag value we integrate up to create our SLSC images. Technically, we know our tooltip size, so with a light profile that is either smaller or larger than the tooltip, we will be able to predict the expected spatial coherence lengths and use that to our advantage to maximize tooltip contrast when performing the integration to make SLSC images. We can also use this theory to improve photoacoustic-based robotic visual surveying methods similar to the methods that you saw earlier for biopsy guidance. And although I've discussed our theory in the context of SLSC imaging, we can actually apply and extend it to any photoacoustic method that utilizes spatial coherence. So in summary, there's a wide range of possible applications for guidance of surgeries and procedures with photoacoustic imaging. I did not have time to discuss them all, but I refer you to any one of these publications for more information on this wide range of applications featured here and explored by my lab. I also want to leave you with the thought that photoacoustic guided surgery has a bright future, and I invite you to check out this video that was created by the Maryland Science Center in honor of my Outstanding Young Engineer Award. It shows a lot of the technology that I described in action. I also invite you to check out these two publications that were recently published, one in the Journal of Applied Physics that talks about photoacoustic imaging for surgical guidance, the principles, applications, and it contains some thoughts on my outlook on the future for the technology. The second publication was produced as part of my invited talk at the 2020 IEEE International Ultrasonic Symposium, and this paper focuses more on the integration of the coherence theory with the optical simulations and how we can use that to design complete systems for surgical guidance. I also draw your attention to this call for papers to an upcoming feature issue to appear in Biomedical Optics Express on the topic of translational photoacoustic images. Submissions are accepted now through December 1st, and I am one of the feature editors. And we actually are discussing extending the deadline by a month or so. So if you're interested, there's still time. So in the Pulse Lab, we follow this unending cycle that integrates optics, acoustics, and robotics to engineer novel imaging systems that address unmet clinical needs. We do this by developing theories and using models and simulations like the one shown here to design novel beamformers and imaging probes, such as this specialized side-firing light delivery system shown here. We then use these designs to build and test prototypes with the goal of improving both ultrasound and photoacoustic image quality. And then we can integrate these unique prototypes with commercially available system components, such as a laser, an ultrasound machine, or a robot. And this integration results in novel imaging systems that are the first of their kind to be tested and interfaced with patients treated at the Johns Hopkins Hospital. We then might learn something from our clinical studies that will require us to revisit our theories, models, and simulations, and then the cycle continues from there. So in conclusion, I've shown you how optimizing photoacoustic images for surgical guidance requires innovations in both light delivery methods and beamforming methods. I also show you how a well-developed theory can fuel our innovation. I've given you a feel for some of the impacted surgeries, such as neurosurgeries, hysterectomies, biopsies, and cardiac catheterization procedures. And I've also shown you how robotic surgical tasks will inherently benefit from these advances. And finally, I would be remiss to end this presentation without saying thanks to my dedicated team of students and collaborators who have helped to make all of this possible. Thanks to my funding sources for supporting this work, and thank you all for your attention. I'd be happy to take any questions.
Thank you so much, Dr. Bale, for the wonderful talk. Question from the audience?
I have a quick question. That was a great, fantastic talk. On your theorem, I remember from my graduate student days of studying Van Sittert-Zernike theorem.
Oh, you know the theorem, cool.
Yeah, but is there, if I recall right, there was some kind of assumption about you having to be in the far field or some distance related to the size. Is there a similar assumption in your theorem?
Yes, we definitely use that same assumption where it only holds true for the far field region And that is true for both the acoustic result and for the photoacoustic result. So in ultrasound, that theorem plays out as us needing to be at the focus of the image, like the ultrasound image focus. And in photoacoustic imaging, we are sufficiently far away from our detectors because for our photoacoustic guided surgery applications, our transducers are externally placed.
Thanks.
You're welcome.
Great.